Okay, so the first couple of questions here you should be able to answer based on activities 4, and then on the next slide, activity 5, and our results in there. From those activity, you should have seen when we had 3 bulbs in series, or I think the activity took us all the way up to 4 bulbs, that our resistance increased. And we knew that because the compass deflection showed that the current decreased. Okay? Now, something that is going to be useful for us is to get to know what our total resistance is. So think about it. If the resistance increases as you add more resistors, how do you think you'd find the total resistance of this particular circuit? And let's say that R1 is 10 ohms, right? This stands for ohm, which is the unit of a resistor. R2 will be 15 ohms, and R3 will be 20 ohms. All right? I'm hoping this one you kind of have this gut feeling that, like, well, let's add those together. So it's exactly how you do it for series, okay? So this is a series circuit, and the total resistance for series is your resistors all added together. Okay, so if you were to think of this as just kind of a generic equation, okay, it's every single resistor added together, and the Rn just stands for, it depends on how many resistors you have. You can have 12 resistors, you can have 2, you can have 150 in a row in series. But no matter how many there are, all you do is add them together. Okay, so in this case, our equivalent resistance, or our total resistance for the circuit shown, would be 10 ohms plus 15 ohms plus 20 ohms, or 45 ohms. Now, something that I'm going to train you to do is, when you do find equivalent resistance, is to redraw your resistor as a single one. Okay? And the squiggly line is just the schematic version of a resistor. And that's something standard you'd see in any class. It's in a circuit with a battery, some zigzag lines stands for a resistor. Okay? And that's our equivalent resistance, or you could call it our total resistance because it's for the whole circuit. Okay? Let's talk about parallel branches. We saw opposite information in our circuit, in our Castle Kit Activity 5. In this case, when we had parallel branches, so light bulbs and separate branches from the main circuit, we saw the resistance go down, and we knew that because our current, the compass deflection, went up. Okay, so for this one, the equation's a little bit more complicated. It's 1 over your total resistance, and this is for parallel, equals 1 over R1 plus 1 over R2 plus plus 1 over Rn. So let's say we have the same resistors. We have 10 ohms, we have 15 ohms, and we have 20 ohms. Okay. We set that up, 1 over RT. It's going to be equal to, and I'm going to teach you how to plug this into your calculator so you don't end up having to separately find these fractions and then go back in and add them in. If you type it in, 10, and then you should have a button. It's usually close to the x squared button that says x to the negative 1. Essentially what that button is, it's an inverse button. It takes your number and does 1 over it. Okay? So if you type it in exactly like this, plus, oops, sorry, I did it out of order here. If you plug it in like that, you get 1 over RT equals 0.216 repeated. Okay? Now, is that our total resistance? I'm hoping you are noticing that we are still dealing with an inverse. Okay, so once you've done all the addition, you can just do the X -1 button one more time. And that gives you a total resistance of 4.62 ohms. And if we redraw our equivalent resistor, would be just a single resistor of 4.62 ohms. Now, something to keep in mind when doing parallel, RT must be less than your smallest resistor. Smallest resistor. Okay, so if you think about it, our smallest resistor was the 10 ohms, 4.62 smaller than that, then we're okay. Okay, so just be really, really careful. Probably the most common mistake anybody's ever going to make is forgetting to do that X to the -1. So with your packet, I want you to try doing, the front page. See if you can get through that. The resistor, the fourth one in the top part that has a series and a parallel. See if you can figure it out, but pause the video. I'll show you how to solve compound or complex resistors that have both types in there in the next portion of the video. Okay, so if you flip in your packet to the second to last page, so like page 5 essentially, it says complex resistor worksheet. This is sample A, and then I'll also do B on the next slide. But for compound resistors, you have to think of these in terms of a charge, okay? And that'll help you break down where you can apply series and where you have to apply parallel, okay? So if you think about it, a charge, and while a charge can originate anywhere, just so that it kind of seems like we have a start and an end, we'll start from the battery, and if you remember, the long side of the schematic is the positive end, and the other side is the negative end. So say we started with a charge that was in the wire right here. It would go to this point, okay? And then at this juncture, it has a choice. It can go down through A, or it can go through the other loop, okay? So it may decide to go down through A, or it could go through B, C, and D, and then get to this other juncture where everything is fed back to the battery. Okay? So, based on that, you should have an idea of, we have two branches here. We have a branch that includes A, and then we have a branch that includes B, C, and D. All right? So these two branches are going to be parallel to each other. However, B, C, and D are not parallel among themselves. So let's think about if our starting point was here. This charge, if it decides to go in the BCD branch, it is forced through B, forced through C, and forced through D, which means at this point, there's only a single pathway. Once it decides to go through the top branch instead of the branch going down, it has to go through B, C, and D. So B, C, and D are series. Okay? And let's see, based on the information given, we know that A is 1 ohm, B is 2 ohms, C is 3 ohms, and D is 4 ohms. When I get to complex resistors, I try to see if I can find any groups of series resistors, because it's really easy to reduce that down to 1. We know that since B, C, and D, if the electron goes through that pathway, it's forced through all three of those. We can add those three resistors together and break it down into 1. Okay? So R, B, C, D, if we make that an equivalent resistor, is going to be 2 ohms plus 3 ohms plus 4 ohms, or 9 ohms. Okay? So I'm going to redraw that with BCD as a single resistor. So here's A, here's BCD. Okay? And then we know A is still 1 ohm, and BCD is 9 ohms. So now I drew BCD parallel to A because that was still the option from going through A. So BCD turned into one equivalent resistor is parallel to A, so our last step is applying our parallel rule. So 1 over RT equals 1, negative 1. All right, so when you see me write negative 1, that means using that x to the negative 1 button, okay? Plus 9, negative 1. And then how do we make sure that we're going to solve for RT? Hopefully you are saying at the end, we apply the negative 1 button again, and then it's RT equals that, okay? So 1, negative 1, 9, negative 1 is 1.11, and then if we do negative 1 again, you get 0.9. Now, is that less than our smallest resistor? Our smallest resistor was 1, so yes, we're good. So we'll redraw our circuit one more time, and our final equivalent resistor is going to be 0.9 ohms. Okay? So let's go do B. So this is B. And again, I like to look for things that are in series first because that's easy. All you have to do is add them and then figure out parallel. Okay? So we know A is 1 ohm, B is 2 ohms, C is 3 ohms, and D is 4 ohms. Let's trace our electron pathway. So our electrons have to go through A and B, okay? And then here they have a choice. They can go through C, or they can go through D. And then once they get back to this other juncture, they go back, every electron goes back to the battery, okay? So what this tells us, every single electron has to go through A and B, so A and B are in series. Now, electrons have a choice of going through either C or D, so C and D are parallel. All right, so let's take care of our series group. So our AB is going to be equal to 1 ohm plus 2 ohms, or 3 ohms. So if we redraw, we'll have one resistor, and then we still have C and D, C, D, and then this we'll call AB, okay? And then, so this is going to be 3 ohms, this is still 3 ohms, and this is still 4 ohms. Then if we want to take our two parallels, because we know what to do with them, and figure out what CD is. Our CD is equal to 1 over 3. Actually, I'm not going to write it that way. I'm going to keep you in your format with the calculator. 3, negative 1, plus 4, negative 1. And what do we do to get it so that it's RCD equals? We can get rid of that 1 over if we do our inverse again. Okay, 3, negative 1 plus 4, negative 1, negative 1 gives us 1.71 ohms. So if we redraw our resistor one more time, we'll have something that looks like this, an AB, which is 3 ohms, and CD, which is 1.71 ohms. And then, if you think about this equivalent resistor and where the electrons would have to go, they are forced through AB and through CD. So now these equivalent resistors are in series with each other. So to get our final single equivalent resistor, we take our equivalent is 3 ohms plus 1.71 ohms. And that makes our equivalent resistor 4.71 ohms. Okay? So, Many, especially complex resistors, they take several steps to break them down. All right, if you're not sure what to do, just see if you can find anything where electrons have to pass through more than one. Like there's no way for them to get away from that resistor. Then you know those are in series and you can just add them together. And then if sometimes it's really easy to see parallel branches, so get those down into just one single resistor. All right, oftentimes you end up having to do things, series equivalencies and then parallel equivalencies and then series again and then maybe even parallel again. Okay, this isn't something that's going to be done in one step. But if you have questions, please ask.